Imagine for a moment a world once vibrant, teeming with the very essence of life: water. Not just trickles or frozen caps, but vast shimmering oceans stretching across an entire hemisphere. Now, imagine that world is Mars, the desolate red planet we know today. For decades, humanity has gazed at Mars, captivated by its rusty hues and stark landscapes, dreaming of a time when it might have been a second Earth. We've sent probes, orbiters, and rovers, each meticulously searching for the elusive signs of its watery past, hoping to unlock the secrets of its potential for life. But what if the most compelling evidence for this ancient watery past wasn't found by the familiar names in space exploration, the agencies whose logos adorn our childhood dreams of space? What if it was unearthed by a new, formidable player, quietly, methodically, rewriting the very history of the red planet? This is not a hypothetical. This is the story of China's audacious journey to Mars, a mission that has not only showcased a monumental leap in space exploration capabilities, but has also delivered a discovery so profound it could fundamentally alter our understanding of Mars, its potential for life, and the future of humanity's cosmic destiny. From the vast enigmatic plains of Utopia Planitia, a silent explorer, the Zhurong rover has unearthed a secret buried for billions of years, compelling evidence of an ancient ocean shoreline, a ghost of Mars's watery past. This isn't just another rock sample or a fleeting glimpse of ice. This is a geological fingerprint, a testament to a time when Mars was a very different world, a world that might have been ripe for life. The implications are staggering, not just for science, but for the geopolitical landscape of space exploration. The new space race isn't just about planting flags, it's about finding life, finding resources, and ultimately, finding our place in the universe. Stay with us as we delve into China's groundbreaking Mars discoveries and uncover what they truly mean for the Red Planet and for us. For generations, Mars has captivated humanity's imagination. From ancient myths to modern science fiction, the Red Planet has been a canvas for our hopes, fears, and dreams of life beyond Earth. Its stark, rust-colored landscapes, sculpted by ancient winds and water, whisper tales of a past that might have mirrored our own. But for all our fascination, Mars has remained stubbornly enigmatic, a world of tantalizing clues and unanswered questions. Was it ever truly alive? Did oceans once shimmer under a warmer Martian sun? And if so, what became of them? These are not just academic inquiries, they are fundamental questions that challenge our understanding of planetary evolution, the prevalence of life in the cosmos, and ultimately, our own unique place within it. For decades, the quest to unravel Mars's secrets has been led by a handful of nations, primarily the United States, whose iconic rovers and orbiters have become synonymous with Martian exploration. We've watched with bated breath as spirit, opportunity, curiosity, and perseverance meticulously traversed its craters and plains, sending back breathtaking images and invaluable data. Their discoveries have reshaped our understanding of Mars, revealing a world that was once far wetter and potentially more habitable than its current desolate state. Yet, even with these monumental achievements, the definitive proof of a vast, ancient Martian ocean, a true cradle for life, remained elusive, a tantalizing ghost in the planet's geological record. But now, the narrative of Martian exploration is undergoing a dramatic shift. A new player has emerged on the cosmic stage, quietly, methodically, and with breathtaking speed, challenging the established order and delivering discoveries that are forcing us to reconsider everything we thought we knew about the Red Planet. This is the story of China's audacious journey to Mars, a mission that has not only showcased a monumental leap in space exploration capabilities, but has also delivered a discovery so profound it could fundamentally alter our understanding of Mars, its potential for life, and the future of humanity's cosmic destiny. From the vast, enigmatic plains of Utopia Planitia, a silent explorer, the Zhurong rover has unearthed a secret buried for billions of years. Compelling evidence of an ancient ocean shoreline, a ghost of Mars's watery past. This isn't just another rock sample or a fleeting glimpse of ice. This is a geological fingerprint, a testament to a time when Mars was a very different world, a world that might have been ripe for life. The implications are staggering, not just for science, but for the geopolitical landscape of space exploration. The new space race isn't just about planting flags. It's about finding life, finding resources, and ultimately, finding our place in the universe. Stay with us as we delve into China's groundbreaking Mars discoveries and uncover what they truly mean for the Red Planet, and for us. For decades, the narrative of Mars exploration was largely dominated by a few key players. The United States, with its pioneering Mariner, Viking, and later, its highly successful Mars Exploration Rover and Mars Science Laboratory programs, carved out an undeniable legacy. The Soviet Union, despite numerous challenges, also made significant early contributions. These nations, driven by scientific curiosity, technological prowess, and often geopolitical competition, laid the groundwork for our understanding of the Red Planet. But in the 21st century, a new force has emerged, meticulously and rapidly ascending the ranks of spacefaring nations: China. China's entry into the space arena has been marked by a strategic, long-term vision and an impressive series of achievements. From its first manned spaceflight in 2003 to the establishment of its own space station, Tianwen, China has demonstrated a clear commitment to becoming a leading power in space. Its lunar exploration program, Chang'e, has delivered groundbreaking results, including the first ever soft landing on the far side of the Moon. These successes were not mere technological demonstrations. They were carefully orchestrated steps towards more ambitious goals, with Mars firmly in their sights. The Tianwen 1 mission, whose name translates to Questions to Heaven, a nod to an ancient Chinese poem, was a testament to this ambition. Launched in July 2020, it was an incredibly complex and audacious undertaking. To send an orbiter, a lander, and a rover to Mars, all in a single mission. This was a feat that no other nation had attempted in one go. The mission's objectives were comprehensive, aiming to study Martian morphology, geology, surface material composition, subsurface water ice distribution, and the Martian ionosphere and climate. It was a holistic approach, designed to gather a vast array of data that would significantly advance our understanding of Mars. The journey to Mars is fraught with peril. The vast distances, the harsh radiation environment, and the incredibly precise orbital mechanics required for a successful rendezvous make it one of the most challenging endeavors in space exploration. Tianwen 1 navigated these challenges with remarkable precision, successfully entering Mars orbit on February 10th, 2021. This was a critical first step, allowing the orbiter to conduct reconnaissance and prepare for the next, even more perilous phase: the landing. The landing of a spacecraft on Mars is often referred to as the 7 minutes of terror due to the rapid, autonomous sequence of events that must unfold perfectly for success. For Zhurong, this involved a complex ballet of atmospheric entry, parachute deployment, retro-rocket firing, and a final hover and descent. On May 14, 2021, the lander, carrying the Zhurong rover, performed a flawless soft landing in Utopia Planitia, a vast plain in Mars's northern hemisphere. This achievement made China only the third country, after the United States and the Soviet Union, to successfully soft land a spacecraft on Mars, a monumental milestone that firmly established China as a major player in interplanetary exploration. Once safely on the Martian surface, the Zhurong rover, named after the Chinese god of fire and war, began its mission. Zhurong is a 6-wheeled, solar-powered rover, weighing approximately 240 kilograms. It is equipped with a suite of advanced scientific instruments, including a multispectral camera, a ground-penetrating radar, a magnetic field detector, and a meteorological station. Its primary mission was to explore its landing site, analyze the surface and subsurface composition, and search for evidence of past or present water. It was a silent, tireless explorer, meticulously traversing the Martian landscape, gathering data that would soon begin to unravel some of Mars's deepest secrets. The stage was set for a discovery that would not only rewrite textbooks, but also ignite new questions about the red planet's past and future. The 21st century space race is a far more nuanced and complex affair than its Cold War predecessor. While the US and Russia remain major players, the field has expanded to include new national agencies, private corporations, and international consortiums, each with their own motivations and goals. This multipolar landscape fosters both intense competition and unprecedented opportunities for collaboration. China's rise as a space power is a defining feature of this new era, and its Mars program is a powerful symbol of its long-term strategic vision. China's journey to Mars was not a sudden sprint, but a marathon, built upon decades of incremental progress and a deep commitment to mastering the fundamentals of spaceflight. The nation's space program, often operating with a level of secrecy that contrasts sharply with the public-facing approach of NASA, has been characterized by a steady, methodical climb. From the development of its Long March rocket family to the establishment of its own satellite navigation system, Beidou, China has systematically built the technological infrastructure necessary for deep space exploration. The Change Lunar program served as a crucial proving ground, allowing China to test and refine its capabilities in orbital mechanics, soft landing, and robotic exploration. Each successful lunar mission, from the first orbiter to the groundbreaking landing on the far side of the Moon, was a stepping stone towards the ultimate goal, Mars. The Tianwen 1 mission was the culmination of this long-term strategy. Its all-in-one design, combining an orbiter, lander, and rover, was a bold statement of intent. It showcased China's confidence in its technological prowess and its ambition to leapfrog into the top tier of spacefaring nations. The orbiter was designed to provide a global survey of Mars, mapping its surface, studying its atmosphere, and searching for signs of water ice. The lander and rover, meanwhile, were tasked with in situ exploration, providing ground truth for the orbiter's observations and conducting detailed scientific analysis of the landing site. This integrated approach allowed for a comprehensive, multi-layered investigation of Mars, maximizing the scientific return of the mission. The Zhurong rover itself is a testament to China's engineering capabilities. Named after the god of fire in ancient Chinese mythology, a name that evokes both the fiery entry into the Martian atmosphere and the fiery spirit of exploration, Zhurong is a robust and versatile platform. Its six-wheeled design, similar in some respects to NASA's Spirit and Opportunity rovers, allows it to traverse the challenging Martian terrain. Its solar panels provide the necessary power for its operations, and its suite of scientific instruments is designed to address key questions about Martian geology, mineralogy, and the potential for past or present life. The ground-penetrating radar, in particular, was a key innovation, allowing Zhurong to peer beneath the surface and reveal the hidden history of Utopia Planitia. The successful operation of Zhurong and its subsequent discoveries have not only provided invaluable scientific data, but have also demonstrated China's ability to conduct long-duration, complex robotic missions on another planet, a capability previously demonstrated only by the United States. Zhurong's landing site, Utopia Planitia, is far more than just a vast, flat plain. It is a region steeped in Martian history and scientific intrigue, a prime target for any mission seeking to understand the red planet's watery past. Utopia Planitia, Latin for plain of nowhere, is one of the largest impact basins in the entire solar system, spanning an astonishing 3,300 kilometers in diameter. Its sheer scale alone hints at cataclysmic events in Mars's ancient past, but it's what lies beneath its surface and what scientists have long hypothesized about its history that makes it so compelling. For decades, planetary scientists have theorized that Utopia Planitia was once home to a vast ocean, a northern sea that may have covered a significant portion of Mars's northern lowlands billions of years ago. This hypothesis was born from observations of ancient shorelines, geological features, and mineralogical evidence suggesting the widespread presence of liquid water on early Mars. If Mars truly had a warmer, wetter past, then these northern plains, being the lowest elevations, would have naturally collected vast amounts of water, forming a Martian ocean. The sediments deposited in such an ocean would hold invaluable clues about the planet's climate history, its geological evolution, and crucially, its potential for harboring life. The choice of Utopia Planitia for Zhurong's landing was therefore no accident. It was a strategic decision, driven by the desire to directly investigate these long-standing hypotheses. The region offered a relatively flat and safe landing zone, crucial for a mission of this complexity, but more importantly, it promised access to geological layers that could confirm or refute the ancient ocean theory. Scientists hoped that Zhurong's instruments, particularly its ground-penetrating radar, could peer beneath the surface and reveal the hidden stratigraphy, the layered history of this enigmatic plain. Landing on Mars, however, is never a simple affair. Even with a carefully selected site, the Martian atmosphere, though thin, is dense enough to cause significant drag and heating during entry, yet too thin to provide much lift for parachutes. The terrain, while appearing flat from orbit, can hide treacherous rocks and craters. The entire entry, descent, and landing sequence, often referred to as EDL, is a ballet of precision engineering and autonomous decision-making, executed in a matter of minutes, light years away from human control. For Zhurong, successfully navigating this perilous sequence and touching down gently in Utopia Planitia was a triumph of engineering, opening the door to the scientific revelations that would soon follow. The rover was now positioned in a location that had been whispered about in scientific circles for decades, a place where the echoes of an ancient Martian ocean might still resonate beneath the dusty surface. The stage was set for Zhurong to begin its silent quest, to listen to those echoes and translate them into a story of Mars's profound past. With Zhurong safely on the surface of Utopia Planitia, the real work began. The rover, a marvel of engineering, was equipped with a suite of instruments designed to peel back the layers of Martian history. While its cameras provided stunning visual panoramas and its spectrometers analyzed surface composition, one instrument stood out as particularly crucial for unlocking the secrets of Utopia Planitia: the ground-penetrating radar, or GPR. Imagine an archaeologist, not with a shovel, but with a device that can see through the earth, revealing buried cities and ancient artifacts without disturbing a single grain of soil. That, in essence, is what Zhurong's GPR allowed scientists to do on Mars. The GPR works by sending electromagnetic waves into the subsurface and then listening for the echoes that bounce back. Different materials and geological layers reflect these waves differently, creating a unique signature that can be interpreted to reveal what lies beneath. Zhurong's GPR was capable of probing to depths of up to 100 meters, offering an unprecedented look into Mars' shallow subsurface. As Zhurong traversed the dusty plains, its GPR meticulously scanned the ground beneath. The data it collected began to paint a remarkable picture. Scientists observed distinct, layered structures in the radar profiles, extending for vast distances. These layers were not uniform. They showed variations in thickness, composition, and arrangement. Crucially, these patterns bore a striking resemblance to coastal deposits found on Earth, the kind of layered sediments that accumulate along ancient shorelines, deltas, and beaches where water bodies once existed. Think of the stratified sands and silts you might find along an old lakebed or a fossilized beach. Zhurong was seeing the Martian equivalent. The scientific interpretation of these findings was profound. The layered sediments, with their specific characteristics, provided compelling evidence for the presence of a buried ancient ocean shoreline in Utopia Planitia. This wasn't just a suggestion of water. It was a geological signature of a large, standing body of water that persisted for a significant period in Mars's early history. The GPR data indicated that these deposits were likely formed by the action of water, laying down sediments over time, much like how rivers deposit silt into a lake or ocean, or how waves sculpt beaches. This discovery is a game changer. For years, the idea of a vast northern ocean on Mars was a tantalizing hypothesis, supported by geomorphological features visible from orbit, such as ancient river valleys and potential paleo shorelines. However, direct, unambiguous evidence from the subsurface was lacking. Zhurong's GPR provided that crucial missing piece, offering a direct look at the internal structure of these deposits and confirming their aqueous origin. It moved the ancient Martian ocean from the realm of theory to the undeniable reality of geological evidence. While other missions, such as NASA's Perseverance rover in Jezero crater, have also found compelling evidence of ancient lakes and river deltas, Zhurong's discovery in Utopia Planitia offers a different, yet equally vital, perspective. Perseverance is exploring a specific lake basin, providing detailed insights into a localized watery environment. Zhurong, on the other hand, has provided evidence for a much larger, potentially hemispheric-scale ocean, fundamentally altering our understanding of Mars's global hydrological cycle and its capacity to sustain widespread liquid water. It suggests that early Mars was not just intermittently wet, but potentially had a vast, stable body of water, a true ocean, for extended periods. This distinction is critical, as a large, stable ocean would have provided a far more conducive environment for the emergence and evolution of life than transient lakes or rivers. The red planet, it seems, was once far bluer than we ever dared to imagine. While the discovery of an ancient ocean shoreline in Utopia Planitia rewrites Mars' deep past, Zhurong's scientific contributions didn't stop there. The rover also provided intriguing evidence of water activity on Mars in more recent geological times, challenging the long-held assumption that liquid water is almost entirely absent from the Martian surface today, except for transient brines in specific conditions. These findings push the boundaries of our understanding of Mars' current hydrological cycle and, crucially, its potential for extant microbial life. Zhurong's instruments, particularly its multispectral camera and its onboard spectrometer, detected hydrated minerals within the surface materials, especially in and around sand dunes. Hydrated minerals are those that contain water molecules within their crystal structure, indicating that they formed in the presence of liquid water. The presence of these minerals in relatively young geological features, like dunes, suggests that water was present and active on the Martian surface much more recently than the ancient ocean. This isn't evidence of flowing rivers or standard lakes, but rather hints at processes like the melting of subsurface ice or the formation of thin films of briny water that could have interacted with the regolith. Furthermore, Zhurong's GPR, in addition to mapping the ancient shoreline, also provided insights into the distribution of subsurface water ice. The radar signals revealed distinct patterns consistent with the presence of ice layers beneath the surface, particularly in the mid-latitudes of Utopia Planitia. These findings corroborate previous orbital observations that suggested significant reservoirs of water ice in these regions. The detection of geometrically shaped clumps of Martian soil and ice, often referred to as polygons, further supports the idea of freeze-thaw cycles and the presence of subsurface water ice. On Earth, similar polygonal patterns are formed in permafrost regions where water in the soil freezes and thaws, causing the ground to crack and deform. The implications of these more recent water discoveries are profound. If liquid water, even in transient or briny forms, has been present on Mars' surface or shallow subsurface in relatively recent geological times, it significantly increases the possibility of extant microbial life. Life as we know it requires liquid water, And if Mars has provided even fleeting opportunities for its existence, then the chances of finding microbial communities clinging to survival in protected niches beneath the surface or within briny pockets are enhanced. These findings provide tantalizing targets for future astrobiological missions, guiding them to specific locations where the conditions for life might still persist. However, detecting extant life on Mars is an immense challenge. The Martian surface is bombarded by harsh ultraviolet radiation, and its thin atmosphere offers little protection. Any life forms would likely need to be extremophils, adapted to survive in incredibly harsh conditions, possibly deep underground or within protected microenvironments. The instruments required to detect such life are complex and must be designed to avoid contamination from Earth-based microbes. Despite these challenges, Zhurong's findings provide a renewed sense of optimism and direction for the ongoing search for life beyond Earth. They tell us that Mars is not entirely dry and dead. It still holds secrets of water, and perhaps of life waiting to be uncovered. The red planet, it seems, continues to surprise us with its enduring hydrological activity. A beacon of hope in the vast cosmic desert, Zhurong's discoveries, particularly the evidence of an ancient ocean shoreline in Utopia Planitia, are not just isolated findings. They are crucial pieces of a much larger puzzle that is forcing scientists to fundamentally rewrite the history of Mars. For decades, the prevailing view of early Mars depicted a planet that was perhaps intermittently wet, with transient lakes and rivers, but not necessarily a world with vast, stable bodies of liquid water. Now, that picture is dramatically changing, painting a far more optimistic scenario for the red planet's past habitability. The emerging narrative suggests that early Mars, billions of years ago, was a far warmer and wetter place than its current desolate state. This period, often referred to as the Noachian epoch, roughly 4.1 to 3.7 billion years ago, saw a Mars with a much thicker atmosphere, capable of sustaining liquid water on its surface for extended periods. Evidence for this warmer, wetter past comes from numerous sources. The widespread presence of ancient river valleys and deltaic deposits observed from orbit, the discovery of clay minerals that form in the presence of water, and now, Zhurong's direct subsurface evidence of an ancient ocean. This convergence of evidence from multiple missions and different scientific instruments is incredibly powerful, solidifying the case for a truly watery early Mars. The role of liquid water in the emergence and sustenance of life cannot be overstated. On Earth, water is the universal solvent, the medium in which biochemical reactions occur, and a fundamental component of all known life forms. If early Mars indeed harbored a vast ocean, it would have provided a stable, long-lived environment, a prime crucible for the potential emergence of microbial life. The presence of such an ocean would have created a complex hydrological cycle, with precipitation, runoff, and evaporation, further enriching the planet's potential for habitability. This isn't just about the presence of water, it's about the duration and stability of that water, which are critical factors for life to take hold and evolve. Zhurong's findings integrate seamlessly into this evolving timeline of Martian water. The ancient ocean shoreline in Utopia Planitia provides direct evidence for a significant body of water during the Noachian epoch, suggesting that the northern plains were not just occasionally flooded, but were home to a persistent ocean. The subsequent discoveries of hydrated minerals and subsurface ice suggest that water continued to play a role in shaping the Martian landscape, albeit in different forms. Even as the planet transitioned to its colder, drier state. This paints a picture of a Mars that didn't just lose its water overnight, but rather underwent a prolonged and complex hydrological evolution with different phases of water activity. This nuanced understanding is crucial for targeting future missions and understanding the full scope of Mars's past habitability. Drawing parallels with Earth's early history can be illuminating. Our own planet, in its infancy, was also a hot, volcanic world, gradually cooling and forming oceans where life eventually emerged. While Mars' smaller size and weaker gravity meant it couldn't hold onto its atmosphere and water as effectively as Earth, the fact that it may have had a similar, albeit shorter-lived, period of warmth and wetness is incredibly significant. It suggests that the conditions necessary for life might not be as unique to Earth as once thought, and that the universe could be teeming with planets that, at some point in their history, were capable of supporting life. This expands our cosmic perspective and makes the search for life beyond Earth even more compelling. However, the question remains, what happened to all that water? The prevailing theory is that Mars lost its protective magnetic field early in its history, leaving its atmosphere vulnerable to erosion by the solar wind. Without a thick atmosphere, the planet's surface water would have either evaporated into space or frozen into subsurface ice. Zhurong's findings of subsurface ice and hydrated minerals are consistent with this scenario, suggesting that a significant portion of Mars's ancient water might still be locked away beneath its surface, waiting to be discovered. This makes the red planet not just a relic of a bygone era, but a potential reservoir of resources for future human exploration, and perhaps a hidden sanctuary for microbial life. The story of Mars is far from over. It's a saga of transformation, loss, and enduring mystery, with each new discovery adding another compelling chapter to its complex and fascinating past. The detailed understanding of this transition from a wet to a dry Mars is crucial for understanding planetary evolution in general, and for predicting the habitability of exoplanets. The discovery of an ancient ocean shoreline and evidence of more recent water activity on Mars by the Zhurong rover intensifies humanity's most profound quest: the search for extraterrestrial life. If Mars once harbored vast oceans, and if water persisted in some form for longer than previously thought, then the chances of life having emerged, and perhaps even enduring, on the red planet increase dramatically. But what exactly are scientists looking for, and how do Zhurong's findings guide this monumental search? The primary goal in the search for Martian life, past or present, is to identify biosignatures. These are any substances, structures, or patterns that are indicative of biological activity. Biosignatures can take many forms: fossilized microorganisms, complex organic molecules that are uniquely produced by life, isotopic ratios that suggest biological processes, or even specific patterns of chemical disequilibrium that cannot be explained by geological processes alone. The challenge lies in distinguishing true biosignatures from abiotic, non-biological geological processes, which can sometimes mimic the signatures of life. Zhurong's discovery of ancient coastal deposits in Utopia Planitia provides an ideal target for future astrobiological investigations. On Earth, ancient shorelines, and marine sediments are rich repositories of fossilized life. The layered sediments found by Zhurong's GPR could potentially contain preserved remnants of Martian microorganisms, if they ever existed. Future missions could be designed to drill into these specific layers, retrieve core samples, and analyze them for microscopic fossils or complex organic molecules. The presence of hydrated minerals in these layers further enhances their astrobiological potential, as these minerals can act as protective matrices, preserving delicate organic compounds over geological timescales. Furthermore, the evidence of more recent water activity, even in transient forms, opens up the possibility of extant life on Mars. While the surface of Mars is extremely hostile to life as we know it, protected subsurface environments, such as those containing water ice or briny pockets, could offer refugia. Microorganisms on Earth thrive in extreme environments, from deep-sea hydrothermal vents to the frozen deserts of Antarctica. It's conceivable that similar extremophils could exist beneath the Martian surface, shielded from radiation and harsh surface conditions. Zhurong's findings of subsurface water ice and polygonal structures point to such potential habitats, making them prime targets for future missions equipped with advanced life detection instruments. These discoveries are not just academic, they directly influence the design and objectives of future Mars missions. The scientific community is already planning Mars sample return missions, a highly ambitious endeavor to bring Martian rock and soil samples back to Earth for detailed analysis in terrestrial laboratories. Zhurong's identification of specific high-priority locations, such as the ancient shoreline in Utopia Planitia, provides invaluable guidance for where to collect these samples. Bringing samples back to Earth would allow scientists to use a far wider array of sophisticated instruments with much greater sensitivity than can be deployed on a rover, significantly increasing the chances of detecting subtle biosignatures. Beyond robotic exploration, Zhurong's findings also have profound implications for human exploration of Mars. The presence of significant subsurface water ice, confirmed by Zhurong's GPR, is a game-changer for future human missions. Water is not just essential for drinking and growing food. It can also be split into hydrogen and oxygen, providing breathable air and, crucially, rocket fuel. If human explorers can extract water from the Martian subsurface, it dramatically reduces the amount of mass that needs to be launched from Earth, making long-duration missions to Mars far more feasible and sustainable. Utopia Planitia, with its confirmed water ice reserves, could become a prime location for future human outposts, a stepping stone for humanity's expansion into the solar system. The search for life on Mars is more than just a scientific endeavor. It is a philosophical journey that touches upon our deepest questions about our place in the universe. If life is found on Mars, even microbial life, it would fundamentally alter our understanding of biology, evolution, and the prevalence of life in the cosmos. It would suggest that life is not a unique terrestrial phenomenon, but a natural outcome of cosmic processes, potentially arising wherever conditions are suitable. Zhurong's quiet, methodical exploration has brought us one step closer to answering this monumental question, pushing the boundaries of our knowledge and inspiring a new generation to look to the stars with renewed hope and curiosity. The red planet, once thought to be barren, now whispers tales of ancient oceans and the enduring possibility of life, beckoning us to continue our relentless quest. The geopolitical implications of China's burgeoning space program, and particularly its successes on Mars, extend far beyond mere scientific prestige. They are intricately woven into the fabric of international relations, technological competition, and the long-term strategic interests of nations. The new space race is not simply a rerun of the Cold War era. It is a multifaceted competition involving a broader array of actors, including powerful private companies and driven by a wider range of motivations, from economic gain to national security. China's approach to space exploration has been characterized by a blend of strategic patience and rapid execution. Unlike the more open and collaborative model often espoused by NASA and its European partners, China's program has historically operated with a greater degree of national autonomy and less international integration. This has allowed it to develop indigenous capabilities across the entire spectrum of space activities, from launch vehicles and satellite constellations to deep space probes and human spaceflight. The Tianwen 1 mission, with its ambitious all-in-one design, was a powerful demonstration of this self-sufficiency, showcasing China's ability to execute complex interplanetary missions without relying on external assistance. This rise has naturally sparked concerns in some quarters, particularly in the United States, about a potential shift in the balance of power in space. The fear is that China's rapid advancements could lead to a technological and strategic advantage, potentially impacting areas like satellite navigation, space-based surveillance, and even future resource extraction on celestial bodies. The rhetoric often frames this as a zero-sum game, where one nation's gain in space comes at the expense of another's. This perspective has led to policies like the Wolf Amendment in the US, which largely prohibits NASA from engaging in bilateral cooperation with China, creating a distinct divide in international space efforts. However, another perspective argues that the new space race, while competitive, also presents opportunities for a different kind of engagement. The sheer scale and complexity of exploring and eventually settling other planets are so immense that they may ultimately necessitate international cooperation. The scientific community, in particular, often champions the idea of open data sharing and collaborative missions, recognizing that the universe's mysteries are too vast for any single nation to unravel alone. Imagine the accelerated pace of discovery if all major spacefaring nations pooled their resources, expertise, and scientific data. The potential for breakthroughs in understanding Mars, and indeed the entire solar system, would be exponentially greater. China's discoveries on Mars, by providing concrete evidence of past habitability and crucial resources like subsurface water ice, will undoubtedly influence future mission planning across all space agencies. The identification of Utopia Planitia as a region rich in water ice makes it a prime candidate for future human landing sites, potentially leading to a scramble for access and resource utilization. This necessitates a robust international dialogue on space governance, resource allocation, and ethical considerations for planetary protection. Who owns the resources on Mars? How do we ensure that scientific exploration is prioritized over commercial exploitation? What are the rules of engagement for human missions to other planets? These are complex questions that require global consensus, not unilateral action. Furthermore, the success of China's Mars program serves as an inspiration for other emerging space nations. Countries like India, Japan, and the United Arab Emirates are also making significant strides in space exploration, demonstrating that the capabilities once exclusive to a few superpowers are becoming more widely accessible. This democratization of space, while adding layers of complexity to international relations, also promises a future where more diverse perspectives and scientific approaches contribute to our collective understanding of the cosmos. Ultimately, the future of space exploration and humanity's place within it will depend on how these geopolitical dynamics play out. Will the allure of scientific discovery and the shared human quest for knowledge transcend national rivalries? Or will the new space race become another arena for terrestrial power struggles? China's success on Mars is a powerful reminder that the exploration of space is no longer the exclusive domain of a few. It is a global endeavor, with profound implications for science, technology, and the future of our species. The Red Planet, once a distant dream, is now a tangible frontier, and the nations of Earth are vying for their place in its unfolding story. The question is not just what China found on Mars, but what humanity will find there, together or apart. The path we choose in the coming decades will define not only our relationship with Mars, but also our relationship with each other as we venture further into the final frontier. As we conclude this journey to the Red Planet, guided by the silent, tireless work of China's Zhurong rover, we are left with a profoundly altered understanding of Mars. The question of what China found on Mars has yielded answers that resonate far beyond the scientific community, touching upon our deepest aspirations for discovery, our understanding of life's potential, and the evolving dynamics of humanity's reach into the cosmos. We've seen how China's methodical approach, culminating in the ambitious Tianwen 1 mission, has firmly established it as a formidable force in space exploration. The successful landing of Zhurong in Utopia Planitia was not just a technological triumph, but a strategic placement in a region long hypothesized to hold the keys to Mars's watery past. And Zhurong delivered. Its groundbreaking use of ground-penetrating radar unveiled the unmistakable geological signature of an ancient ocean shoreline, buried beneath billions of years of Martian dust. This discovery is a powerful testament to a time where Mars was a very different world, a world potentially teeming with liquid water, a prime candidate for the emergence of life. Beyond the ancient past, Zhurong also provided tantalizing clues about water on modern Mars, detecting hydrated minerals and subsurface ice in relatively recent geological features. These findings open new avenues for the search for extant microbial life, guiding future missions to protected niches where life might still cling to existence. The implications for human exploration are equally significant, with subsurface water ice representing a vital resource for future outposts, transforming Mars from a distant dream into a tangible destination. Zhurong's discoveries have forced us to rewrite Mars history, painting a picture of a warmer, wetter, early Mars, a planet that underwent a complex hydrological evolution. This revised narrative not only enhances the prospects for past life, but also informs our understanding of planetary habitability beyond Earth. And finally, These achievements have underscored the geopolitical shifts in space exploration, highlighting China's growing influence and sparking renewed discussions about competition, collaboration, and the shared human endeavor to explore the unknown. Yet, for all the incredible discoveries, Mars remains a planet of enduring mystery. The exact nature of its ancient ocean, the precise timeline of its water loss, and the ultimate fate of its potential life forms continue to be subjects of intense scientific inquiry. Was the ancient ocean truly vast and long-lived enough for complex life to evolve? What mechanisms led to the planet's dramatic climate change? And most profoundly, does life in some form still exist beneath its surface, waiting to be found? These lingering questions are not a sign of failure, but a testament to the boundless nature of scientific exploration. Each answer we uncover only reveals new questions, pushing the boundaries of our knowledge further into the cosmic unknown. Mars, with its ancient secrets and its enduring allure, continues to beckon us, challenging humanity to reach higher, dig deeper, and dream bigger. The journey to the Red Planet is far from over. It is an ongoing saga of discovery, resilience, and the relentless human spirit of exploration. Join us as we continue to delve into the depths of the cosmos, unraveling its mysteries, one mind-bending concept at a time. The universe is calling, and its stories are just beginning to unfold. Be part of the journey, subscribe to Cosmo Depth, and together, let's explore the wonders that lie beyond. The cosmos awaits, and its secrets are slowly but surely revealing themselves to those who dare to look.